Welcome back to the deep dive. This is where we take the source material you provide and really dig into it to pull out the key insights for you.
That's right.
Today we've got something pretty specific. The ISOC Advanced and AI Audit Official Review Manual. You brought this to us.
Yep, a core resource for many.
And our goal for this deep dive is to unpack the foundational stuff in Chapter 1. We're talking the overview section in Part A.
Exactly. Think of us as your guides, walking you through this foundational material. It's crucial for anyone needing to get their head around AI systems from that audit, governance, and risk angle.
So you gave us the manual, and we're here to extract what really matters, explain it, make sense of it for you.
And connect the dots. Why does this definition matter? How does this risk fit into the bigger picture? That's what we'll cover.
Okay, then let's unpack this. We're going to look at why this manual exists, how it's put together to help you learn the importance of Chapter 1 specifically.
Which is pretty significant, as we'll see.
And then really get into the weeds on AI models, the different types, how they learn, the whole life cycle, and those crucial business factors.
Yeah, it's a fascinating field, constantly changing, but these fundamentals are key. You really can't audit what you don't understand, right?
Absolutely. You need that baseline understanding of how it's built, how it should work in the business. Chapter 1 really sets that stage.
Right.
So first things first, what is this manual exactly? Who's it aimed at?
Okay, so the source itself is quite clear. The ISAC Advanced in AI Audit Official Review Manual is specifically for people preparing for the ISAC Advanced in AI Audit exam.
Right.
It's positioned not as the only source of truth, not the single authority,
Right.
but more like a comprehensive collection. It brings together information and, importantly, experience from professionals working in AI audit.
And you mentioned it's not something you just pick up off the shelf.
Correct. It's an internal ISAC publication for exam candidates, not generally available publicly. And importantly, it comes with the standard disclaimers. ISAC isn't guaranteeing you'll pass the exam just by reading it.
That context is useful. It
Yeah.
tells you this is a study aid built from collective wisdom, meant to build understanding and skills. It's not like a legal text or just a list of answers.
Exactly. And that collective wisdom aspect is important. It draws on global experience, which is vital in a field like AI that's moving so fast and looks different in different places.
And the way the manual itself is structured, it seems designed to make that learning process easier. There's a consistent pattern in each chapter.
Yeah, that structure is definitely helpful. Each chapter starts with an overview, then lays out the domain content, outline what specific topics are covered.
Okay.
Then you get learning objectives or task statements. These tell you exactly what you should be able to do after studying the material. Very practical.
Skills focused, not just knowledge recall.
Right. Then, suggested resources if you want to dig deeper. Self-assessment questions, crucial for checking your understanding.
With answers and explanations, I assume.
Yes, absolutely. Answers and explanations, which is key. Then the main content section itself. And finally, a list of definitions for key terms used in the chapter. It's a really solid framework for study.
It certainly sounds like a clear roadmap. And it even gives advice on tackling the exam questions that kind of hints at what they're looking for.
It does. The questions are typically multiple choice. You get a STEM, that's the question or the scenario, and 4 possible options.
And often scenario-based, you said?
Yes, very often. They want you to apply the concepts to a situation, not just parrot-back definitions. It's about practical application.
Makes sense for an audit qualification. What's the recommended approach to answering?
Pretty standard, but good exam practice. Read the question STEM carefully. Really understand what it's asking. Look for keywords like best or most, which signal you need to pick the optimal answer, not just a correct one.
Because often more than one option might seem plausible.
Exactly. So read all the options first. Don't jump at the first one that looks okay. Then maybe reread the STEM and the options together and choose the one that best answers the specific question in that context.
It highlights that need for nuanced judgment, choosing the most appropriate path, which is core to auditing, isn't it?
Absolutely. Evaluating situations, weighing factors, choosing the best course, that's the skill. And the manual also makes a point that studying is vital, but so is real-world practical experience.
Right, the theory needs the practice.
Yeah, both for the exam and just for being an effective AI auditor. The fact that experienced pros from around the world contribute to the manual kind of underlines that value of practical insight.
Okay, good context. Now let's get into Chapter 1 itself. The title is AI Governance and Risk. That immediately tells you the focus isn't just techie detail.
Definitely not. It's about oversight, management, control from an organizational viewpoint, and understanding, well, the potential downsides, the risks.
And this chapter carries some serious weight in the exam.
It really does. The manual breaks down the exam domain weightings. Domain 1, which is this chapter, AI governance and risk, makes up 33%, a full third of the exam.
Wow, okay, so this is foundational.
Absolutely. Domain 2, AI operations, is the biggest chunk at 46%.
Yeah.
And Domain 3, AI auditing tools and techniques, is 21%. So getting these governance and risk concepts right is critical.
So what exactly should an auditor be able to do after mastering this chapter? The manual lists learning objectives or task statements, right?
Yes. And these are really the heart of it. They spell out the required capabilities. An AI auditor needs to be able to
Okay.
evaluate the impacts, opportunities, and risks when you bring AI solutions into the audit process itself. So using AI for auditing.
Using AI to audit AI or just general audit?
Both, potentially.
Yeah.
But the focus here is integrating AI into your audit work. Second, actually utilize AI solutions to make audit processes better, more efficient, more effective.
Okay, so actively applying AI in audits.
Right. Then stepping back, evaluate the role AI plays in the organization's decision-making systems. How is it influencing choices?
Critical. What else?
Evaluate the organization's AI policies, procedures, compliance programs, basically, the whole governance framework around AI. Is it adequate? Is it followed?
Assessing the rules of the road for AI.
Exactly. Also, evaluate how AI-specific metrics, KPIs, KRIs, are monitored and reported. Are they tracking the right things?
Performance and risk indicators tailored to AI.
Yes. And finally, a really big one. Evaluate data input requirements for the AI models. This includes looking at whether the data is appropriate, checking for bias, and considering privacy implications.
That data piece seems a fundamental.
It underpins almost everything in ML-based AI. So those objectives really frame the auditor's role, the key questions you need to ask.
And the self-assessment questions help test that understanding. Maybe looking at a couple could make these concepts more concrete.
Good idea. They usually give you a little scenario. Let's take the first one from the overview section. It deals with who does what in AI oversight. It asks which function is typically handled by finance or executive management, while the AI steering committee focuses on strategic advice. The options are A, budget authorizations, B, evaluating AI opportunities and risk, C, managing AI deployment, and D, technical evaluations.
Okay, so distinguishing roles. What's the answer?
The answer is A, budget authorizations. The manual's explanation clarifies this. The AI steering committee looks at strategy, prioritizes initiatives based on risk and opportunity, aligns things with the business goals.
The big picture view.
Right, but the final say on funding, on allocating the actual money, that usually sits with finance or the top executives. Managing deployment or doing technical deep dives. D, that's more for IT or dedicated AI teams. The steering committee is governance strategy, not execution.
Got it. So the steering committee advises and prioritizes, but doesn't hold the purse strings or manage the build. That makes sense from a governance separation perspective. Understanding those roles is key for an audit.
Definitely. You need to know who's accountable for what.
Okay, what about the second question? You mentioned it touched on risk.
Yes. Question 2 gets right into bias. It asks, if an AI solution shows discrimination based on gender in its decisions, what type of bias is the most likely explanation? Options are A, systemic bias, B, statistical bias, C, human bias, and D, overfitting.
Ah, a very hot topic. Bias in AI. What does the manual say is most likely here?
The answer is A, systemic bias. The explanation points out that systemic bias comes from biases that are already embedded in our processes, our institutions, or crucially, in the historical data used to train the AI.
So the AI learns the biases that already exist in the world or the data?
Precisely. It reflects existing societal inequities related to things like gender, race, etc. If the data shows historical discrimination, the AI might learn and perpetuate it. The manual stresses how important it is to spot and mitigate this.
Why not the others? Statistical bias, for instance.
Well, statistical bias, according to the source's distinction here, is more about things like sampling errors. Maybe your data just isn't representative. That's a problem. But systemic directly addresses the embedded societal prejudice causing gender discrimination in this scenario. Human bias is about individual judgments, maybe on labeling data, but systemic bias is broader, baked into the system or data source.
And overfitting.
Overfitting, as we'll discuss more later, is about the model learning the training data too specifically, noise and all. It performs badly on new data. While bias data could worsen overfitting's effects, overfitting itself doesn't inherently explain discrimination based on a category like gender. Systemic bias is the more direct cause, according to the manual's explanation here.
That's a really important distinction. The bias isn't necessarily a new problem created by the AI, but often an existing societal problem reflected and potentially amplified by the AI because of the data or processes it learned from. Critical for an auditor to trace that back.
Absolutely. You need to look beyond just the algorithm to the data's origins and the context.
Let's do one more question from this intro section.
Okay, the third one is about security. It asks what an IS auditor would most likely recommend to enhance threat detection for an AI solution. Options. A, focus monitoring during operation. B, review threat assessment during development deployment. C, increase monitoring across all connected systems. D, report on emerging external threats.
Enhancing threat detection specifically for the AI. What's the recommended action?
The answer is B, review threat assessment during AI solution development and deployment. The logic is about being proactive. Thinking about threats and vulnerabilities early when you're building and planning to deploy the AI lets you build in security from the start.
Security by design.
Exactly. Attackers might target AI even during development or integration, while monitoring during Operation A, wider system monitoring C, and threat intelligence D are all important for ongoing security. The most direct way to enhance detection specifically related to the AI system itself is to do that threat assessment early and design controls accordingly.
So, identifying likely attack vectors or vulnerabilities for this specific AI system during its creation is key to setting up the right defenses and detection later. Makes sense. Proactive is better than reactive.
And often cheaper in the long run. For an auditor, it means checking if that threat modeling is actually happening as part of the AI development process.
Excellent. Those questions definitely help illustrate the practical application of these governance and risk ideas. Okay, let's shift gears now into part A of Chapter 1. This is where the manual starts laying down the technical foundations, AI models, considerations, requirements, getting the vocabulary right.
This is where we define our terms. Part A kicks off with the basic definition of artificial intelligence itself. The manual describes AI as essentially an advanced computer system that can mimic human capabilities, things like analysis, learning, making inferences, deciding
Like
things.
simulating human intelligence.
Right. And it highlights two main ways AI systems work. There's the older approach, using explicit if-then rules, like classic expert systems.
Programmed logic.
Yes. And then the more modern approach, using statistical models that learn patterns and rules directly from data.
Which is where machine learning comes in.
Exactly. And the source identifies the key components here: machine learning, ML, deep learning, DL, and generative AI, GNAI. There's a diagram, figure 1.1, that shows AI as the big umbrella, ML is a part of AI, and DL is a specialized part of ML. Data science overlaps with all of this.
That hierarchy helps. So most of what we call AI today is really ML.
Largely, yes. The manual emphasizes that most current applications use machine learning. They rely on statistical models trained on data to make predictions or decisions when they see new data. So understanding ML is really fundamental for auditing AI now.
Okay, so section 1.1 then starts categorizing AI further. Different types based on what they can do.
Yes, categorized by functionality or capability. Figure 1.2 of the manual outlines 4 main types based on function.
Let's hear them.
First, reactive machines. These are the simplest. They only work with the current input, no memory of the past. They just react based on their programming. Think Deep Blue, the chess computer. It saw the board state now and reacted. Didn't remember past moves or opponent strategy. Or simple spam filters applying rules to one email at a time. Basic industrial robots doing the same task over and over.
What's their main limitation then?
No learning from experience. They can't adapt based on past interactions. They do what they're programmed to do for the current situation. That's it. Like a very smart but memoryless tool.
Okay, so limited use for complex, evolving tasks. What's next?
Second is limited memory AI. This is a big step up. These systems can store some past information for a limited time and use it to inform current decisions. It's not long-term memory or deep understanding, but it allows context.
This sounds like most AI we encounter now. Self-driving cars needing to know where other cars were a second ago, virtual assistants remembering the last thing you asked, chatbots keeping track of the conversation.
Exactly. Recommendation engines using your recent clicks. This ability to hold on to recent history makes them much more capable for tasks that unfold over time. But from an audit view, it also means thinking about how that temporary memory is managed, secured, potentially biased.
Right, new risks associated with that memory. Okay, what are the other two types? They sound more futuristic.
They are. The manual lists theory of mind AI as a future concept. This would be AI that could understand human thoughts, emotions, beliefs, intentions basically, have a sophisticated understanding of mental states and social interaction. We are nowhere near that yet,
Sounds like science fiction AI.
pretty much. And the fourth type goes even further, self-aware AI. Also future concept. This is AI that would possess consciousness, self-awareness, subjective experience like humans. Deep philosophical waters, and again, not something we have now.
So for auditors today, the real focus is on those first two. Reactive machines, though, may be less common now as complex systems, and especially limited memory AI, which drives a lot of current tech.
That's right. The manual also briefly mentions Super AI, ASI, artificial superintelligence based on Figure 1.3.
What's that?
That's another theoretical idea. AI that surpasses human intelligence not just in specific tasks, but across all cognitive abilities. The kind of AI that fuels discussions about existential risk or the future of humanity. Important context, but distinct from the AI we build and audit today.
Okay, bringing it back to practical AI models we see now, Part A discusses generative and predictive models specifically. Let's start with generative, section 1.1.3.
Right. Generative models are all about creating new, original content. This could be text, like writing an article or code.
Or images, music, even synthetic data.
Exactly. Things that didn't exist before, generated by the AI. They learn the underlying patterns and structure from massive data sets of existing examples.
Like learning the rules of language or art from seeing lots of it.
Precisely. And then they use that learned understanding to generate novel outputs that fit those rules or patterns. The manual mentions Jan's generative adversarial networks as one way they work.
Ah, yes, the generator and the discriminator.
Right. One network generates the content, the other tries to tell if it's real or fake. They compete, pushing the generator to get better and better at creating realistic output. It's a clever setup.
But powerful creation tools bring risks, right?
Huge risks. The manual flags several. The potential to generate harmful or illegal content, the deepfakes, disinformation, hate speech, major ethical concerns around authenticity and misuse, and massive questions around intellectual property, who owns the generated content. Did the AI infringe copyright by learning from protected data?
Those are serious audit concerns. You need to look at the training data provenance, the controls on output, the usage policies.
Absolutely, it's a complex risk landscape.
Okay, so that's generative AI. What about predictive models, section 1.1.4?
Predictive models have a different goal. They use historical data and ML techniques to forecast future events or predict outcomes or classify things.
So analyzing the past to predict the future, like credit scoring, predicting loan default, fraud detection, predicting if a transaction is dodgy.
Exactly. Or predicting machine failure in manufacturing, forecasting sales, predicting patient risk in healthcare. Lots of applications. They learn patterns in past data and use those patterns to make predictions about new, unseen data.
What's the key risk here, according to the manual?
The main risk highlighted is the reliance on potentially flawed predictions. If the historical data was biased or incomplete, or the model itself isn't accurate or robust.
Then the predictions will be wrong or unfair.
Correct. And if important decisions are based on those flawed predictions, you can have serious negative consequences, financial losses, unfair treatment of people, missed opportunities. So auditors really need to scrutinize the model's accuracy, its reliability, its fairness, and the quality of the data it learned from.
That link between a technical model flaw and real-world business or societal impact is critical for the auditor to grasp. Okay, moving deeper into the mechanics, section 1.2 focuses specifically on machine learning AI models.
Right. Reinforcing ML as that subset of AI, where systems learn from data without explicit programming for every single outcome. It's about algorithms finding patterns and improving with experience, meaning more data.
And the manual links ML strongly to data science.
Yes, it positions ML as a core tool within data science. And it reiterates why understanding how these ML models learn is so important for auditors. It helps you spot potential weaknesses, sources of bias, limitations, the inherent risks.
And these models need a lot of data.
They're data hungry, yes. They typically need large, diverse data sets, big data, to train effectively. The quality, the representativeness, the sheer amount of that training data is absolutely fundamental. Garbage in, garbage out is very true for ML.
So data quality audits become paramount. Section 1.2.1 then introduces the three main ways ML models learn the basic paradigms: supervised, unsupervised, and reinforcement learning.
These are the foundational approaches. Let's break them down. First, supervised learning. The key here is labeled data. You feed the model training examples where each input is paired with the correct output or label. The model learns to map inputs to outputs.
Like our spam filter example earlier, email input, spam not spam label, the model learns the connection.
Exactly. You need that ground truth in your training data. Supervised learning is often used for two main kinds of tasks. Regression, where you predict a continuous number like house price or temperature.
Predicting a value.
Right. And classification, where you assign things to distinct categories like spam not spam, cat dog image, customer churn no churn.
What are the challenges? The manual mentioned the need for labeled data.
That's the big one. Getting high quality, accurately labeled data can be really hard, time-consuming, and expensive. And there's a risk if the labels themselves are biased, or if the real-world data the model sees later doesn't match the label training data well. Auditing the labeling process is key.
Okay, that's supervised. What about unsupervised learning?
This is the opposite in terms of data. You use unlabeled data.
Yeah.
You just give the model the raw data, and it has to find patterns, structure, relationships within that data on its own without being told what the right answers are.
So discovering hidden structures,
Right.
like finding natural customer segments in purchase data without predefining them.
Exactly. Common techniques shown in Figure 1.4 include clustering, grouping similar data points together, using algorithms like k-means, association rules, finding relationships, like people who buy diapers also often buy beer in retail data, and dimensionality reduction, simplifying complex data by reducing the number of variables while keeping the important info, like PCA.
What are the audit challenges here? Explainability seems like it might be one.
It's a major one. Since there are no predefined correct outputs, it can be much harder to understand why the model grouped things a certain way or found a specific pattern. Is it a real insight or just a random correlation in this data set?
A black box problem, potentially.
It can be, which is why the manual emphasizes the need for human-in-the-loop (HITL) validation. You need humans to review the outputs, make sense of the patterns, check if they're valid and useful, and ensure they aren't based on spurious factors or hidden biases. HITL adds that layer of validation and trust.
So human oversight is critical for unsupervised results.
Right.
Got it. What's the third paradigm?
Reinforcement learning. This is different again. It's about learning through trial and error by interacting with an environment. An AI agent takes actions, gets feedback as rewards or penalties, and learns a strategy, a policy, to maximize its total reward over time.
Like training a robot to walk or an AI to play a complex game, learning by doing.
Precisely. Path planning for robots, optimizing moves in Go or chess, some aspects of autonomous driving. The manual mentions policy-based methods, learning the strategy directly, and cue learning, learning the value of actions and states as approaches.
The trial and error part sounds potentially risky in the real world.
It definitely is. The risks involve the agent potentially taking unsafe or unexpected actions while it's learning, especially if the environment is complex or unpredictable. Ensuring safety during training and deployment, maybe using simulations first, is a huge focus and a key audit area. How do you constrain the trial and error safely?
Right. Okay, so those are the three main learning styles. Section 1.2.2 then brings in neural networks. These seem fundamental to a lot of modern ML.
They are. Neural networks are computational systems inspired by the structure of the human brain interconnected nodes or neurons in layers. They're very powerful for finding complex, nonlinear patterns in data. They learn by adjusting the strengths of the connections between neurons based on the data they process.
And figure 1.5 shows that basic structure. Input layer takes data in, hidden layer do the processing, output layer gives the result.
That's the basic feed-forward structure, yes. The hidden layers are where the complex feature learning happens, and the manual then defines deep learning, DL, as simply using neural networks with many hidden layers. That depth, shown conceptually in Figure 1.7, allows them to learn features hierarchically. Meaning the first layer might learn simple features like edges or corners in an image. The next layer combines those into textures or simple shapes. The next combines those into parts of objects, and so on, up to identifying complex objects. It builds understanding layer by layer.
So deep learning, machine learning with deep neural networks. And there are different types of these networks for different jobs. Figure 1.6 mentions some.
Yes, tailored architectures work better for certain data. Examples include feed-forward networks, simplest type, data flows one way. Good for basic classification regression, like that spam filter again. Recurrent neural networks, RNNs, have loops allowing information to persist, giving them memory. Great for sequences, text, speech, time series. Used in translation, speech recognition. Convolutional neural networks, CNNs, especially good for grid-like data, mainly images. Use special convolution layers to find spatial patterns, powerhouses for image tagging, object detection, medical image analysis.
And the big advantage of deep learning, the manual says, is this automatic feature extraction.
Right, you don't need humans to meticulously craft the input features from raw data, like pixel values or audio waves. The deep network learns the relevant features itself through training. That's why they achieve state-of-the-art results on many complex perception tasks.
But that power comes with a cost, the black box issue.
It often does. Because the network learns these complex hierarchical features automatically, the internal representations within those many hidden layers are often not easily interpretable by humans. It can be very hard to say exactly why the network made a specific decision. That lack of transparency is a major challenge for auditing, explainability, and trust.
Which leads us neatly into section 1.3 on algorithms, the actual recipes the models use.
Exactly. Algorithms are the step-by-step procedures, the computational instructions that the AML models execute to learn from data, find patterns, and make those predictions or decisions. They are the engine of the learning process.
And their behavior is controlled by things called hyperparameters.
Correct. Hyperparameters are like settings or dials on the algorithm that you configure before training starts. They control how the algorithm learns things like the learning rate, how big a step the model takes when updating its connections, the number of layers in a neural net, the complexity allowed. Getting these right is crucial for good performance. It's often more art than science.
So ML models use these algorithms tuned by hyperparameters to learn and adapt. And figure 1.8 just shows examples of different algorithms for different learning types.
Yeah, it gives examples like linear regression for supervised, k-means for unsupervised, q-learning for reinforcement, just illustrating the variety. The choice depends entirely on the problem and the data.
Okay. And then figure 1.9 highlights a really critical risk related to training algorithms, overfitting.
Yes, overfitting is a fundamental problem auditors must understand. It happens when your model learns the training data too well. It basically memorizes the specific examples, including any random noise or quirks in that particular data set.
So it aces the practice test but fails the real exam.
Perfect analogy.
Yeah.
Performs brilliantly on the data it was trained on, but fails miserably when it sees new, unseen data because it hasn't learned the general underlying patterns, just the specifics of the training set.
Why is that such a big risk for auditors?
Because an overfit model is useless, or even dangerous, in the real world. It won't generalize. Its predictions on new data will be unreliable. Auditors need to check what steps were taken during development to prevent or detect overfitting, things like splitting data into training, validation, and test sets using regularization techniques, etc. Figure 1.9 visually shows that performance gap. Great on training, poor on testing.
Got it. Crucial concept. Okay, so we've covered AI types, learning paradigms, neural networks, algorithms, overfitting. Now let's zoom out to the big picture, the AI life cycle, section 1.4.
Right. This section talks about the entire journey of an AI system, from cradle to grave. The manual uses the OECD AI lifecycle model, shown in Figure 1.10, which is a widely recognized framework.
What are the stages in that model?
It lays out these key phases: plan and design, collect and process data, build or adapt models, test, evaluate and validate, operate and monitor, and finally, decommission.
A standard kind of project life cycle, but applied to AI.
Pretty much. But the crucial point the manual makes is that the risks aren't the same at each stage. They change, evolve. What's risky during data collection might be different from risks during operation.
Which implies you can't just audit at the end.
Absolutely not. Auditing needs to consider controls and risks across the entire life cycle. Let's quickly walk through what happens at each stage and the audit angle based on the manual.
Okay, stage 1.
1.4.1, plan and design. This is where it all starts. Defining the concept, the business goals, the requirements, how you'll measure success. Critically, from an audit perspective, this is where you should be identifying potential risks, upfront ethical risks, bias risks, privacy, accountability, who is responsible. Stakeholder input is vital here.
Get the foundations right, including risk assessment. Next.
1.4.2, collect and process data. We've said data is key. This stage is about gathering it and getting it ready for the model, cleaning, transforming, etc. The huge risk here, as the manual states, is bad data. Biased, incomplete, inaccurate, irrelevant data can poison the whole system. Auditors need to scrutinize where the data comes from, how it's collected, how it's processed. Data governance is critical.
Okay, then you build the model.
1.4.3. Build or adapt models. Yep. Selecting algorithms, training the model, tuning those hyperparameters we mentioned. Explainability, understanding why the model predicts what it does becomes important here. The manual notes that the good logging during this stage can create an audit trail. And again, human in the loop, HITL, is highlighted for things like validating model behavior or guiding training, improving robustness and security.
So HITL isn't just for unsupervised learning.
No, it can be valuable throughout, depending on the context, to inject human expertise and oversight. Then comes testing.
1.4.4 test, evaluate, validate. This sounds like a prime audit focus area.
Definitely. This is where you check if the model actually works as intended and is reliable. The manual lists key types of testing. Performance, is it accurate, fast enough? Stress testing, how does it handle unusual inputs or load? Comparative analysis, how does it stack up against benchmarks? Bias and fairness testing, does it discriminate? And robustness security testing, can it be easily fooled or attacked? Auditors need to assess the thoroughness and rigor of this testing phase.
Ensuring the testing covers the key risks. What about after deployment?
1.4.5, operate and monitor. The model is live. Now you need ongoing monitoring. Is performance degrading over time? This is called drift. Are there unexpected outputs? New security threats? You need feedback loops and processes for retraining or updating the model. Auditors check if this monitoring framework is in place and effective.
And the final stage.
1.4.6, decommission. Taking the AI system offline, making sure it's retired securely, compliantly. What happens to the model? The data. Any residual risks? Secure disposal or archiving is important.
So auditing AI really means looking at the controls and risks woven through all these stages. It's a continuous view, not a single snapshot.
Exactly. You need that life cycle perspective. Ignoring a stage means missing potential problems.
Okay, that brings us to the last section of Part A, Section 1.5, Business Considerations. Why is understanding the business side so vital for an AI audit?
Because AI doesn't exist in a vacuum. It's built or bought to serve a business purpose. Auditors need that context to assess if the AI is appropriate, effective, and managed correctly within the organization. Section 1.5.1 covers understanding the business use case, needs, scope, objectives.
What specifically should auditors understand here?
Things like, what actual problem is this AI trying to solve? What's the expected business value? How does it fit into existing processes? Where does its data come from? What other systems does it depend on? What are the timelines? What risks did the business already identify? Have they thought about ethical impacts? How will users adopt it? Knowing all this helps scope the audit appropriately.
Makes sense. The audit needs to align with the business reality. The manual also mentions cost-benefit analysis 1.5.2.
Just briefly, it notes that AI CBAs can be tricky. Benefits might be hard to quantify, tech changes fast, and there can be hidden costs like data sourcing or fixing unexpected problems. An auditor might look at how robust that initial CBA was.
Then there's the deployment choice. Internal versus cloud hosting. 1.5.3, figure 1.12. What are the trade-offs?
Key differences in risk profile. Internal hosting. You control everything, hardware, software, data. Potentially better security privacy if your internal controls are strong, data stays put. But higher upfront costs, need specialized staff, might be harder to scale up or down quickly. Cloud hosting. Highly scalable, lower initial costs usually. Provider handles infrastructure. But less direct control. Vendor lock-in risk. Network becomes critical. Big one. Privacy and security implications of sending your data outside your walls to the cloud provider requires strong contracts and oversight.
So the deployment choice significantly impacts the control environment an auditor needs to assess. Data location, vendor reliance, infrastructure control all change.
Absolutely. And speaking of vendors, Section 1.5.4 talks about managing them. Crucial, since many AI solutions are bought, not built. Auditors need to look at vendor assessment during onboarding, checking their risk management, ethics, transparency, security, and ongoing, monitoring SLAs, performance compliance. Understanding the vendor's own AI strategy is also a helpful context.
This seems especially relevant when using cloud AI services or off-the-shelf AI tools, which leads directly to the final point. Shared responsibility, 1.5.5. This sounds important.
Extremely important, especially with third-party AI. The idea is that when you use an external AI solution, whether it's a model from a vendor, AI services on a cloud platform, or an app with embedded AI, the responsibility for making sure it works correctly, securely, and compliantly is shared. It's not just the vendor's problem, and it's not just yours.
So you can't just outsource the risk entirely.
Definitely not. You need crystal clear agreement on who is responsible for what. The manual highlights the risks, if this isn't clear. Accountability gaps, finger pointing when things go wrong, and data security risks if data sharing isn't handled properly.
Is there an example of how this works?
Yes, the manual uses the Microsoft AI Shared Responsibility Model, figure 1.13. It visually breaks down responsibility across layers. AI usage, how you use the AI application, the specific model code, and AI platform, the underlying infrastructure. It shows how responsibility shifts between Microsoft as platform provider, potentially a custom model builder, model dependent, and the customer. Auditors need to understand this division to check if controls cover all the bases, with clear ownership.
That visual makes it clear the customer always has responsibilities, especially around usage and the data they provide, even with vendor solutions.
Precisely. You retain significant responsibility. Identifying those boundaries and ensuring controls exist on both sides of the line is a core audit activity.
Wow. Okay, that was a really thorough walkthrough of those foundational elements. We cover the ISACA manual's purpose and structure.
The importance of Chapter 1 on governance and risk, and what auditors need to be able to do, using those self-assessment questions to illustrate concepts like governance roles, systemic bias, and proactive security.
Then we really dove into Part A, defining AI, the different functional types, the distinction between generative and predictive models with their unique risks.
And the core ML learning paradigm, supervised, unsupervised, reinforcement how they learn, their challenges like labeled data needs, explainability gaps needing HITL, and trial and error risks. Plus neural networks, deep learning, algorithms, hyperparameters, and that critical risk of overfitting.
We wrapped up with the AI lifecycle perspective, the need to audit across all stages, from planning to decommissioning, and the essential business context. Use cases, cost-benefit, hosting choices, vendor management, and that crucial shared responsibility model.
It really paints a picture of how multi-layered AI auditing needs to be. You need the technical grasp, the data understanding, the process view via the life cycle, the business context, and the awareness of responsibility lines. These fundamentals are the absolute bedrock.
Couldn't agree more. You can't effectively assess risk without this foundation.
Absolutely necessary before diving into specific audit tools and techniques.
So thinking about everything we've just unpacked, the complexity, sometimes the opacity of these models, the insidious nature of systemic bias hiding in data, the tangled web of shared responsibilities, how does all this really challenge our traditional ways of auditing? What new skills or maybe even, fundamentally different mindsets do you think auditors need most critically now to navigate this landscape and genuinely ensure trust and accountability in AI?
That really is the million-dollar question, isn't it? The required skill set is certainly evolving, moving beyond traditional IT audit in many ways. It demands more data literacy, more statistical understanding, maybe even some ethical reasoning skills. It's a fascinating shift.
It certainly is. Well, that brings us to the end of this deep dive into Chapter 1's overview and Part A from the AAIA Audit Manual. We hope breaking down these core concepts has been valuable for you.
Yeah, hopefully that provides a solid grounding.
Join us next time as we continue to unpack complex topics from the source materials you bring us.